Hello and welcome to another episode of Containers from the Couch. I am Justin Garrison, and joining me today is Cy, Shane, and Nathan. We're going to go into intros in just a second, but today we're talking all about Kubernetes API priority and fairness. And I made a quick short to give you an introduction into how that works. And so let's go ahead and kick off with that, and then we're going to dive deep into it. Once I find it, hold on. Where'd it go? There it is. I got you. We got to do it live.
Priority and fairness is how the Kubernetes API protects itself from being overloaded from too many requests. So when the Kubernetes request comes in, yeah, Elmo?
Can I have a snack?
Oh, sure. Here you go. Here, have a snack.
Can you tell me all the United States?
The what?
Yeah,
Right
I
now?
want to know all the states.
Okay. All right, here you go.
Thank you.
All right, so as I was saying, when the request comes in, it has to.
What color is this guy?
It's blue.
Can you show me all the state capitals?
Okay, hold on. All right, Elmo, you asked really short questions, so you can ask two at a time. Okay, put them in here, and I'll get to it as soon as I can. Ernie, your questions are kind of long, so you just ask one. Okay, so put it in here. Now, priority and fairness. Great, this is great. Thanks so much. The toilet is flooded. Okay, so I understand it's hard with all these buckets, okay, but we're gonna add one more, okay? This is the high priority, okay? If anything comes in, it's an emergency, put it in here. This is Flo. Give her the questions and she's gonna put it in the right bucket, okay? I don't think we're gonna have time to talk about.
Amazing.
Flow joke, because there's levels to it.
I know, there is, it's deep.
Let's get into it. So, Cy, thank you so much for joining me today. Shane, why don't you kick it off? Introduce yourself. What do you do at Amazon?
Awesome. Hey, gang, my name's Shane, and I work on the operational side. So, while others will be explaining kind of how API priority and fairness, I'll give you some tools. I've wrote a blog for you that you can understand and how to monitor to see if you're going to have the problem in the first place.
And Nathan, how about you?
Okay, I'm Nathan. I'm from the EKS scalability team. I'm a software engineer there. So our team deals with issues with running Kubernetes at scale, running very large clusters. We deal with issues related to availability, latency, and of course, API priority and fairness, which we'll get into today.
And just so everyone knows, is Elmo in any part of this chain of API priority and fairness?
I mean, you kind of stole our thunder. You explained it already.
But in that, that scratches the surface. So Nathan, can you give us an overview of what it actually does and why it's needed?
Yeah. So the API priority and fairness feature was added in Kubernetes 120, and it's a mechanism to split up API server requests between different users. So before 120, we were in this mode where there's a total number of API server requests that could be handled at a certain time. The default was 600, and anyone could use that share of requests. And the problem was there would be noisy neighbors. You wouldn't be able to allocate which kinds of requests you could serve at a given time. So this new feature, APF, gave us a mechanism to divide requests or to allocate certain shares of requests to those seats. So with 120, for example, if you had one of the high priority requests, you could set aside a share of requests for those to be served.
So just referring back to the short really quickly, we got multiple types of requests there, right, Nathan? So one of the requests was really straightforward from Elmo. I'm guessing that's just like a get request. But then the other request from Ernie, he's got longer requests. So those are list requests. I think that's the best way of putting it there. They're getting multiple requests back. And so requests like that will take more priority, right? They just take up more of the bandwidth, the throughput. And that probably adds to the issue, right? So what sort of issues were people seeing before API priority and fairness was implemented?
So there's multiple parts to it where the number of seats that a request use varies by how expensive the request is. So a GET request, for example, will just occupy one Inflight request for that duration, where a list request it typically has higher latency, it's operating on multiple objects, and it's going to hold those seats for that entire request. So a GET pod request, for example, might just take 500 milliseconds or less, whereas listing all pods across your cluster could be close to 60 seconds or the API server timeout. So part of the problem is these more expensive requests have a higher load on the API server and etcd. So that's really the purpose of this feature, is to protect the server during periods of high load. So when APF rejects a request, what the client sees is a 429 response code indicating that they need to retry their request later. So it's really a mechanism for the server to protect itself and for high priority requests to get through during those times.
So I think you answered the cusp of who would care about this feature, and most people should care, but you probably care more as soon as you start seeing 429s, right?
Yeah. So kind of the two the two side effects of this feature are your request could fail with the 429, and you'd have to try again later. But you could also experience higher latency. Like this feature introduces queuing, and queuing is really a trade-off between I'm fine with adding latency onto my request if it could eventually get served, but that's another side effect of this feature.
Yeah, I know, as Shane's going to explain to us, like queuing's a good thing for like general API safety, and latency isn't always, and dropped calls aren't always like,
Yeah.
oh no, something's wrong. Like that's how the system should work.
And just to suck you into the problem for a minute, let me frame this up. A really common one that happens a lot of times is you're running a batch job, maybe like an ML, and you need to check the statuses on those pods. There's two ways to do that. You could either, hey, kubectl get inside of a pod, right, which is going to be an absolute disaster and send millions of list calls, or do like Nathan's going to show you and do something like a watch where it's a little less. But sometimes you're one Helm deploy away from something that doesn't do that well. Like, some logging agents try to go get metadata for every single log, and it's going to be, not so good. So if you get into a situation where you're not in control of that application, maybe it's someone else's Helm chart, Nathan's going to kind of show you some tools that we can use as kind of like a plan B almost of protecting itself, if that makes sense.
Yeah, let's jump into it. Let's go ahead and see how this works visually, and then do some demos here. And I know there was one question on, is it APF or KPF?
APF, API Priority and Fairness.
There we go. All right, Nathan, you ready for the demo?
Yeah. I think I'll kick it off with just showing a demo or a diagram from the best practices guide.
Nice. Let's see it.
Can you guys see this?
Mm-hmm.
Yep.
Cool.
And I saw comments here, like, don't worry if this is over your head. Like, we're if you have questions, that's what we're here for. Thank you for joining the live stream. We want to answer the questions as we go through it. So if we're talking over your head, please ask questions. We're going to go ahead and try to explain these things.
Yeah, absolutely. So this is a diagram kind of showing the high level flow of the feature. There's kind of two objects within Kubernetes that define how APF works. So the first one is a flow schema, and from Justin's video, that was like literally flow. Like a flow schema maps, or a given request will map to exactly one flow schema. So like a get pod request will map to a flow schema, a watch request will map to one of the flow schemas. And there's kind of two important parts of a flow schema. It's what the request is. So like whether that's a get request for pods or a watch request for pods. And then the other part of it is who is making that request. So is it a pod who is asking for this resource, or it might be an external user, or it might be like a cluster administrator. Those are kind of the two things that determine which flow you end up in. So we can just go through the first flow schema here for service accounts. So this is capturing really any request that authenticates as a service account. And this will be your pods, because pods are using a service account token. If your pods are making requests to the API server, they're going to be mapping to this first flow schema. And then a flow schema, once a request is assigned to a flow schema, it then goes to the next kind of Kubernetes object, which is a priority level configuration. So this second class of objects this is how the actual requests are divided up. So by default, Kubernetes gives 600 in-flight requests at a given time. Those 600 in-flight requests are divided among these priority levels. So workload low, for example, might get somewhere around 250 out of those 600 requests. So whenever pods are making requests to the API server, they're going to be using this bucket, and they're not going to be able to go above that 250 limit. Other buckets, those are going to be used by other users and other types of requests. Did you guys have anything you wanted to jump in or add to that?
So Nathan, when we're looking at these flow schemas, that's kind of this graphic is showing us a few, but these are all very customizable, right? Based on the type of request and that kind of thing. It's basically almost infinite amount of being able to set precedents for which requests flow through which schema and priority level, right?
Yes, yeah. So when you create a new EKS cluster, you'll get the upstream defaults for these objects, and I think there's somewhere between 5 to 10 of each of flow schemas and then priority level configurations. And beyond that, you can add your own flow schemas or your own priority level configurations to make it customizable for your workload. So if I had one type of pod that I would really wanted to prioritize, what I could do is I could add a new flow schema here that captures all those requests from that specific service account, and then I could give it its own share of requests as well. If my pods always require, say, 100 requests, I could create a new priority level that was custom, and then give that all to my custom requests. And the demo will kind of go into an example of how you can use flow schemas to kind of tailor to your workload.
Gotcha.
Quick point on size topic just before we leave this. You can go way overboard with this. Cutting up those buckets, too many of them. I want you to think of shares in a company. There's only 100 shares in that company. And if you start giving every single person a share, something important, you have to take shares from that. Some of these buckets are how like the control components of Kubernetes talk to each other. And if you start stealing and making too many, interestingly enough, Sai, going a little too overboard with that feature, exactly like you talked about, is one way to get into a lot of trouble in this stuff. So just be mindful as you're doing that. Thanks, guys.
And you know, I'll be honest, a lot of this is new to me, and I was reading the docs earlier, and one of the things that I saw was there's a way to set at least a minimum amount of requests per each priority level, right? So even if there was a pod sending thousands of requests and its workload high, that's not going to prevent system calls from getting through because there's a set amount of bandwidth or precedence for system level calls, right?
Yeah, absolutely.
Yeah.
But ironically, right, since the buckets, there's only so many now, whereas before it was a little bit open, you kind of got to watch those buckets a little bit more now, whereas before you kind of didn't because it was kind of a wide open field. So there's some great things and it's really important, but it's a little bit more to take care of now because, more features, more things to look at, right?
Got it. It'd be really cool to see this hands-on because I feel like 99% of people are going to say, look, the defaults sound great. But for the few that may need to change this, it's probably more than 1%. It'll be good to understand where they should start messing around so they don't get themselves into a bad situation.
Yeah, and there's kind of two approaches like to solve this issue. So like just looking at workload low, like if we exceed say we have 250 requests, if we exceed that, what ends up happening is we start queuing requests. So this is where we'll see kind of the two trade-offs of the feature where we'll start requeuing requests and once we exceed the 250, but we're not going to reject them right away. Eventually these could time out within these queues, or the queues could get full, and at that point the client would see a 429. So that's what we're trying to avoid here is how do you make sure that your high priority requests get through without queuing, and then also without added latency. And the first way you could do that is you could modify your workload, and that's usually what we recommend is try to make these settings work with the defaults. And if you could modify your workload such that your request requirements are satisfied within that 200 existing, say 250 limit, then you should do that. Otherwise, we could look into these more specific tweaks with like adding new priority levels. Because ideally, if we modified our workload to use less than 250, that would be a more straightforward change. So I think maybe we could jump into the demo, unless anyone had any more questions about this diagram.
Let's see it here on Containers from the Couch. I think if our viewers have seen our episodes before, we love seeing hands-on, we love seeing demos. So let's get into it, Nathan.
Okay, cool. So I'll just kind of came up with an example situation, just like a hypothetical of how if we're running into 429s, how can we avoid that? So the situation I set up is, suppose we have two users, both using the same share requests. So in this case, we're going to be using the global default bucket. That's not on the diagram, but that is one of the defaults that come installed on your cluster. So that's a share of, it's allocated 49 out of those 600 requests. So we have two users, they're both competing for it. And in this example, one of the agents is making expensive list secret calls. So the EKS cluster I have set up has 50,000 secrets installed. So each one of those requests is going to be trying to list all those secrets. And then the other agent is just trying to create a pod. And because we have 10 of these list secret requests, all listing 50,000 secrets, that's going to use up all of our concurrency for that bucket. And what we're going to see is when we try to create the pod, it's going to be rejected with a 429, and we're not going to be able to create the pod object or get it scheduled. And if that's a critical workload, or if that's some kind of critical function, that could cause some like an outage on your cluster. And then just one thing to note, I'm running this test on a cluster with just one API server, so that we don't have to worry about our requests being routed between two. So whenever I'm issuing a kubectl command, it's hitting the same API server, and we'll be able to see the API or the APF state across that. So do you guys have any questions about that? About like what this is?
That is an important thing to call out here. You have one API server. EKS clusters by default usually have at least two. And so you are going to share those buckets between, it's load balance, and those buckets are basically being transacted by two servers. So depending on how many API servers you have, you increase the amount of processing you can do on those buckets. The same amount of buckets can handle twice as much, as long as it's well balanced, as long as each API server is getting the right amount of requests. So it's really good, like simplify it to understand it here with one API server. But as you go to production with this, be mindful of how many API servers are handling those requests and working on those queues.
Yes, yeah, great call out. So like with the previous example of the pods having 250, in reality, it's going to be 500 total. And as long as you're properly load balancing your requests, you'll have that 500 total to work with a default cluster.
Cool.
Sweet. Yeah. So let me pull up my terminal. So I have a couple scripts prepared to kind of run through that situation. So I'll show the first one. This is a script I put together to do that list secrets call. So this is just a loop that executes 10 times, and it's going to be listing all secrets at global scope. So I'm using kubectl get raw. An equivalent command would be kubectl get secrets -a to get them across all namespaces. Something to keep in mind with default kubectl behavior is it uses pagination by default, which is what we want. So if I would have just did kubectl get secrets -a, it would have just been batching my secrets 500 at a time, where I'm just, for the sake of the demo, I'm trying to make an expensive request. So I'm listing all 50,000 out once.
Well, sure, because no one would do that in production. That's a
yeah.
Be surprised. Yeah.
Yeah, and I can tell off the bat this is not a production bash script, because there's no sleep 1 second in it. Because that's how all production bash scripts end up, with a sleep 1 second in that loop, and then you know it ships to prod. But I love this example here.
Yeah. I mean, this does, so it does wait for it. This kicks off 10 subshells and then waits for each shell to finish. So it might be a little better than a sleep, but yeah, this is by no means meant for production. So what I can do here is let me start the script, and this will kick off the 10 list secret requests all at the same time. And one thing to keep an eye out for is we were talking about list requests are more expensive than other kinds of requests. So each one of these list requests is going to be fetching 50,000 secrets. The number of seats or the number of requests from our bucket it's going to use is actually 10. Whereas cheaper requests are just going to be using 1. So this kind of compounds the issue with we're kicking off 10 list secret requests, but the total concurrency we need is actually going to be not 10 but 100 requests. And the global default bucket we set up only has around 50. So we're going to be only able to serve around half of these requests. And then on top of that, when we try to create our pod, it should be rejected because all of our concurrency is in use until these requests succeed or end up timing out. So let me kick off that request. And then up here at the top, I can I have this other bash script to create a pod, and I'm just creating this simple Nginx pod, and we can see that it's hanging on the kubectl request. I'll just show that script real quick.
I see your other list returned.
Yeah, so at the bottom, I kicked off the 10 requests. I just stopped the script from running because it's going to keep issuing the 10 requests as soon as the previous 10 complete. So those subshells are now completing. These requests either succeeded or got a 429. But on the top terminal here, you could see that it was hanging on trying to create the pod. So what happened when I issued this was it went to the bucket, and then we used all of our concurrency up. And then this request, if I didn't kill it, it would have timed out after 15 seconds in the queue, and it would have failed. So all I was running in that script was this create pod command.
So Nathan, you mentioned it does get inserted into a queue, but it'll fail after 15 seconds. Is there a reason for that? Is that a default? Can that be changed for how long requests can time out for?
Yeah. So there's kind of two timeouts working right here. So there's the default API server timeout. So by default, an API server request will time out after 60 seconds. There's a further timeout enforced when it gets to an APF queue. So if we exceed our concurrency, it ends up in a queue. It can actually only be in a queue for 15 seconds. And then it will time out at that shorter duration. So if it didn't end up queuing, then it would have respected the full 1 minute timeout. Does that make sense?
Gotcha. Yeah. And APF is enabled here, right? And is it using the default configuration that all EKS clusters have today for APF?
Yeah. So this is using the defaults. The global default bucket has 49 seats, and that was the next thing I was going to show is when I'm going to kick off these 10 list secret requests, and I'll dump some APF metrics that show what's the state of the queues and what's going on with those requests. So let me run that again, and then I'm just going to print off some raw metrics from the API server endpoint, and I'll go up to those. So these metrics are just scraped from running from the /metrics endpoint on API server. This is the same thing that can be scraped with Prometheus. I'm just getting the raw dump here. So I think that the two we could talk about here are the concurrency in use versus the concurrency limit. So this is showing how much we're using versus how much this given bucket has. So what our global default bucket has is we're allocated out of the 600 requests, we have 49 of those. So because the list requests are taking 10 seats each, we're actually only able to get 4 of those list requests executed. So concurrency limit 49. If we go up to current executing requests, we can see that's 4 because the 4 times 10 is 40. That's all we're able to use. If we wanted to get 5 executing, that would require 50 seats, which we don't have out of that limit. And then to see how much these 4 requests are actually using, the 4 times 10, that's this other metric here called concurrency in use. So one really good measure to see if you're seeing issues with APF is to compare these two, concurrency in use versus concurrency limit. This will give you how utilized is your bucket, or like how much headroom do you have before you might start running into issues.
Okay, so Nathan, I have to ask, even though you were running that job to get all the secrets, you were able to get the APF metrics. So there's something going on here where we couldn't deploy a pod, but we can get other APIs responding. How does that work?
Yeah, good, great question. So the reason for that is I'm scraping the endpoint with a different user that's going to a different bucket. So if I look at that script where I was like get APF metrics, you can see that I'm using this kubeconfig here. This kubeconfig has system masters permissions, and this user is actually exempt from any APF bucket. So this is primarily for administrators to have a way to get out of issues like this, because like you don't want to completely lose access to your cluster. So if you have a user with system masters permissions, you can use that kubeconfig to help troubleshoot or try to fix your issue. And when you create a new EKS cluster, the cluster creator IAM role gets this permission granted automatically. So each EKS cluster actually has at least one user with this kind of elevated permissions.
Okay, that makes sense.
And is there another way to route, like you mentioned, service accounts and kube control like as a different user? How do you route those with the schema, like which bucket you're going to be directed to? Is that based on just my ID of how I'm calling that, or is that based on what action I'm doing or what API endpoint I'm doing?
Yeah, so when you get mapped to a flow schema, it's two things. It's what am I requesting, and then also who I am. So if I wanted to create a new user, I could add that new user to my AWS auth config map, assign them an identity, and now I can refer to that identity in a flow schema object. So I could do something where I'd say any request from this user is going to be going to this new bucket. Does that answer your question?
Yeah, that was what I wanted to call it. And one other question from DJS here. How do you get more space, more buckets, bigger buckets? Is that just a matter of adding more API servers, or is there something else to do?
Yeah, so with a default cluster, like you are stuck with it's the sum of two flags. It's the max in flight plus your max mutating in flight. And by default, that's 600 requests. So you're going to have to work around those 600 in-flight requests. To increase that, one option would be to horizontally scale the number of API servers. Each additional instance you get, that's going to increase your overall concurrency by 600. Alternatively, you could scale those two flag values. And this is handled by EKS auto-scaling automatically. So as you increase the size of your cluster, you will see more in-flight concurrency to handle your requests.
Right. So in EKS, we can't change those. You can't change those API flags, but as your cluster grows in size based on nodes and based on some other metrics, we will scale your API servers for you to increase some of those limits.
Exactly. Yeah. And it's like how priority levels work is you get a fraction of whatever's available. So it's not like you need to change your priority level objects when you get more in flight. It's going to be allocated across all buckets according to what proportion you want. So even when you come up with more in flight, the relative number of seats between each level will be consistent.
Again, I just want to caution on one thing, right? Hey, I can only do a total of like 500, and I want to set that to 1,000. Please remember that this is a protection mechanism for everything else. So you don't want to infinitely scale this. It's at that limit for a particular reason. And again, what Nathan's showing you is kind of how to define those buckets. So just keep that in the back of mind. I get that request quite a bit.
Yeah, exactly. And that's why we have these limits on like, that's why like smaller clusters are not going to be able to handle the same number of in-flight. And this is a protection mechanism. Like in a world without APF, we would be risking complete unavailability. Like having requests have slightly higher latency latency or having to try again later is preferable to not having an endpoint to reach out to, for example.
Right.
So yeah, thanks for bringing that up, Shane.
Yeah, part of me was thinking this is a security feature too. It's
It is.
at the end of the day a limit against denial of service. It's
I mean, yeah, Kubernetes is literally a denial of service, like as a service, right? Like that's it's a distributed system with an API, and every single component in that distributed system is calling that API for various things. So, yeah. And to John's question, yes, EKS does automatically scale the control plane for you. That's part of the service that we offer.
Yeah. So I'll keep going with the demo. So I think we got an overview of what problem we're trying to solve with how do we get our create requests to go through when we're trying to compete with these list secrets. So there's kind of the two approaches where we can modify our workload or we could modify APF settings. The first thing we should do is try to see if we can optimize our list secret calls, or is there some kind of equivalent call we could make that's cheaper or uses less seats. And typically one of the first things we look at is, can we replace periodic list calls with a more efficient watch? So what watch is a much more efficient way to get changes to collections over time. So we could issue a watch against these secrets, get the initial state, and then we'll be notified whenever something changes. That's a lot more efficient than relisting the complete collection of 50,000, especially if it's like a static collection right, like now where they're not changing very often. So we can do that actually. So I have another script here where instead of listing the secrets, we have this loop here that is issuing 10 concurrent watch requests. Same thing here. I'm doing a kubectl get raw command. A better way to do this with kubectl would be kubectl get secrets and then -- watch, and that will prevent you from having to manually construct this URL. But this just makes it a little more explicit. What we're doing is we want a global watch against secrets. So I'll kick off this request, and then I'll try to create the pod, and then that should be able to get through, because each one of these watch requests will only be using one seat or one share compared to the list requests that we're using 10 each. So in the previous example, we were trying to use 100. In this case, we should be only using 10, which is less than our limit of 49 for this global default bucket. Cool. So let me kick off watch secrets. We kicked off all 10. And then up here, I'll try to create my pod. And then it looks like I had already had it created. But this shows that it went through. Like this got rejected with a 404 because I had left it existing. But if I recreate it here, we could see that the request went through. So because we optimize our requests, now we are able to get those served. And in this case, we're still getting the same information. Like if this client needed a global view of the secrets across the cluster, it's still able to get that with a watch request, but it's able to do so at a much less server intensive manner. And then,
if I can, maybe just because not everyone might understand the nuances of a watch, I want you just to watch for this one simple thing, right? If you see somebody inside of a pod, right, that's deployed on a cluster, doing syntax like get kubectl get pods, right, inside that pod, getting all the other pods, that is one of the most common ways to cause this problem. And there's something called a controller, and there's, Nathan, you probably have a couple of preferences, Justin, everybody on, there's templates that you can use these controllers that turn those kind of requests into a watch, like Kube Builder and stuff like that. So if you see that behavior, try to point that developer in that direction. Nathan, would you say that's kind of your experience as well?
Yeah, absolutely. And most of the time when we're seeing these issues, it's with a client Go. It's not like with a bash script like this. It might be some kind of third-party plugin or something that's being installed on clusters. And a lot of the times, like these might be open stream components where someone doesn't have direct control. So this is really like if you're working on your own controllers or working with client Go, these are best practices to keep an eye out for.
Great.
And so that's a good like for the next part of the demo. I think that's a good point to bring up, Shane. because sometimes like we might not have control over what's necessarily making these list requests. Like if it is a component we don't directly own, or it's like an add-on that we're just installing on our cluster, we might be stuck with either turning off that component completely, or if we need to have that component run and it's still going to be issuing these list requests, what we could do is move those list requests to a different bucket. So now it's going to be going to its own share of requests. In this example, I'll move the list secrets requests over from the global default bucket to the catch-all bucket. The catch-all bucket actually has fewer shares than global default. So it's still going to run into 429s, and only a subset of our list secret requests are going to get handled. But the trade-off is now our create pod call against the global default bucket, that'll be able to be served. So this is one example of workload isolation where we could tune APF to isolate some of the requests that aren't critical, so that it makes room for the ones we need to get through.
Nathan, did you have more in the demo? I know we want to shift over to seeing what Shane has too to help people understand and troubleshoot it a bit more.
Yeah, I'll just I won't actually I'll just show the flow schema example for we could apply this, and then this is going to capture all of our list secrets. I won't go through and actually create it, but so this was the object that we could apply. I called it list secrets custom. So those previous list requests, this is going to be captured by this rule. It's listing secrets at the cluster scope. And then the matching precedence, if a request could match multiple flow schemas, it's going to match the one with the lowest matching precedence. So I'm making sure that this one is actually lower than what it was with the global default bucket. And now it will be shifted over to this new bucket.
Nathan, could we see a kubectl get flow schemas just to kind of see what precedence exists for maybe some of the other schemas?
Yeah. So these are all the default ones that will be installed when you create a new cluster. And then if we wanted to apply a new one, we could do something like this, where we created it from that file I just showed. And now our list secrets custom is applied. And if we get flow schemas, we can see that our custom one is here now. So
what was the precedence of the list previously? The list.
So previously it was matching global default with this 9,900. We just need to make the new flow schema have something less than 9,900. So we could have done 9,800. I just did 9,000 for the example. So now list secrets is matching this rule, and it's going to the catch-all bucket rather than the global default bucket.
Okay, and the create pods, which that would also be global default, or is that somewhere else?
Yeah. So initially they were both going to global default. We just moved the list over to catch-all, and then the create pod call kept going to global default. Okay. So now it wasn't being starved. Yeah.
So it looks like list secrets is at a lower precedence, meaning now it has even higher priority, but is it because it's at a different priority level that enables create pod to go through even if we're doing list secrets?
So the precedent corresponds to when I have a request, which flow schema does it go to? What really matters in terms of importance is the priority level. So the priority level is how many requests I actually have allocated. Catch-all actually has fewer shares than global default. So even though our list secrets call is going to be matching this rule with a higher priority, it's going to be allocated actually a bucket with fewer requests.
Got it. I think I was conflating the precedence and priority level.
Yeah.
That makes sense.
Cool.
Awesome.
Yeah. You want to take over, Shane?
Yeah, sure. Let me just do a quick point on why what Nathan's showing you is so important. You want to fix these problems at the source. So the number one thing to find out is like, what's yelling at your API server that much, right? Is it like the logging agent that we talked about beforehand? I'm going to show you, and Justin, am I sharing my screen right now? Can you guys see that?
There you go.
Great. I'm going to take a look at a few things here. First off, remember, we want to solve a problem at its source. So how would we do that? We can kind of go and look at who's calling our API server on some charts, right? We can see the type of calls that are coming and try to reverse engineer a little bit who's calling. Here's how that would work out. Once you figure out who the villain is in that story, we've got some CloudWatch queries that I'll share with you, basically that you run here, and it'll output what agent is spamming that. And once you've got that villain identified, you can go, a lot of times these open source projects will have a feature that sounds so good. Wait, in my logging, I can get what pod it is or all this Kubernetes data. That sounds amazing. And unintentionally, it starts blowing up the server. It starts blowing up the server. And so by first, do I even have a problem? By looking at a chart, right? Getting the villain kind of identified and turning that feature off. But sometimes, and Nathan's who I call for help, by the way, when you get into trouble, right, you need a plan B. And what Nathan's talking about is I could coordinate that traffic, that villain, into like a flow schema, right, to identify it and put it in a bucket where I'm like, go away, right, and not blow up my server when I need it. That's why what Nathan's showing you is so practical. But how do you know if you got this problem? And can we condense this through pretty pictures? Because that's what I need, right? This stuff's too brain damaging. That's why I got Nathan. Do I have a set of things that I can navigate real simply to know, do I have a problem? Do I need to spend time on this? Now, I'll link a blog, or my friend Cy and Justin will link a blog that I have for you, where basically I'm going to give you the chart that I'm showing you today. And I've got a blog. I'm a little long-winded, right? So bear with me, but I have a blog that goes through all the stuff in the chart and what all the pictures mean and what you want to look for. And I'll give you the chart at the end of the day. But let's take a quick look at, what does this look like? So what I want to do is notice how Nathan was telling us about these different buckets. The default, friends, is pretty good. It turns out all these people, these thousands of developers, they kind of know what they're doing, right? And the defaults are pretty good. But sometimes, friend, you got that thing that's going a little crazy, right? And what you want to be able to do is on a percentage basis, I want to look at this and say, oh my goodness, this particular bucket, and sorry, I didn't spawn a bunch of stuff here, but this particular bucket, workload high, is like at 3.7%, or it's worse, it's at 100%. If you see this bucket, and it's important looking, right? Workload high, system, leader election. If you see leader election is 100%, stop. Now you care about priority and fairness. You got to do something, right? However, if you see something like catch-all at 100% and you see drops, that's okay. That's what this was designed for. It's just because you have drops doesn't necessarily that means that that's a bad thing, because this is a protection mechanism, right? When I get into this stuff, sometimes when I learn about something new, everything is this problem and any drops are bad. You don't want to mess with this stuff too bad, because Kubernetes hates delay, right? There's a lot of things to talk to. And like a line in Disney World, right? As the line gets longer and longer, the longer it takes to get through that line. Kubernetes hates that. Things like webhooks only have a little bit of time that you're allowed to get through a system. And if you overdo that, you break some stuff that's really important. So be careful about oversizing these queues. Be careful about making, you can be a little too fancy for your own good. Ask me how I know. So with that, right, we want to determine, now that we know all this fancy stuff, right, we saw 100%, is this a real problem? Well, or is it a problem with the API server itself? A couple things that I would do. First thing I would do is if I saw this at 100% and my catch-all was super high, right? In this case, it's not, but let's just pretend. See, this is that bucket and the shares that's associated. This is getting not used, but workload low. Look how big that is, right? Well, I don't care about that, but my leader election is getting, it's not enough. Well, I would take shares from here and just put it over here, right, where it's important. That's kind of the 90th percentile of what you'll be doing when you don't have to get into the fancy stuff unless you get in a bad way, like we were talking about earlier. But is your problem priority and fairness to begin with, right? Justin alluded to something really important, right? Hey, What if we pinned up to one API server somehow, some way, for whatever reason, right? How would we be able to detect that? Well, friends, what we have is the ability of these in-flight request charts. So you see, this server wasn't so much where these two server was. If I saw some crazy imbalance, would I spend all my time troubleshooting the API and priority fairness on that one server? No, I wouldn't, right? And where you get into trouble is not to chart shame anyone, but a lot of these charts that we that we develop to look at things like the API server were published before API priority and fairness came out. So it would be so easy just to download a random chart and it looks good, you're feeling good about it, right? But it doesn't actually cover this new system. And that's the thing to be, careful of in like all of Kubernetes type of stuff, right? Is everything's constantly updating and making sure that your charts and all of that type of stuff. So watch those asymmetrical flows. Drops aren't always bad, remember, because this is here to protect, right? And troubleshoot it in tiers, right? Look for those empty buckets to give stuff that you need, right? And realize, right, the number one problem that we run into is what Nathan talked about. And he knows that because he's the one that takes all these calls, right? Of, something's going crazy, right? And it's saying, give me all 100,000 pods, right? Don't just do it once and keep a little cache sitting aside that it's just going to send updates. Some things don't do that in Kubernetes. Metrics are a great example. I'm scraping metrics because you're really good, right? And you're using a horizontal pod autoscaler with some custom metrics, right? Can I cache those metrics? No, I can't, right? Because, they need to be new, right? It's not something that's cacheable, but that's a very important function. So imagine, right? Imagine, you're a support guy that learns this, right? And get a little too aggressive and creative with these queues that drop stuff. And you start dropping those Prometheus requests that are scaling. Do you see how quickly we could get into trouble? So when you do something like this, make sure we're really doing, just because something's spamming an API server doesn't necessarily means it's bad. We want to look for that bad behavior that could have been more efficient. Like, hey, don't do a get pods on 100,000 pods every 30 seconds. That's something that's just straight up inefficient. So think about the thing that you're putting in the workload just a little bit, right?
So yeah. Shane, I wanted to say, so I was wondering, what is this dashboard you're showing? I see it's Grafana, so I looked it up, and I got the tagline for this dashboard is, it's a dashboard for obsessive people.
Yes. So look, I'll tell you, on my journey, right, I can't keep up with the Nathans and all that, but what allows me to punch above my weight class is I can look at the wrong statistics all day and it points me away from the problem. Let me give you a really simple example of this. I just showed you 3 API servers. If I averaged all of those together, guess what that would look like, Sai? If I was looking for the number of errors, I had 0 and 0 on this server and I was totally slamming this one. That average would give me the wrong statistic, right? And so I noticed some people are new to Kubernetes, right, in the chat. And whoever was trying to do their CKA in like 6 weeks or something amazing, put all that aside, right? If you're not spending 6 months getting your CKA, you're doing it wrong. Because at the end of the day, it's not about the cert. It's about like when you get in service, right? Like how much value that you're to add. And you can easily get caught up in all this fancy stuff of web injected, WebAssembly, Envoy and stuff. But if you had some time to spend, right? Site, Prometheus, Grafana, understanding what these metrics are and stuff like that, and what that will do for you, right? That'll cut about 3 years of learning off my Kubernetes career, right? Is it's going to point you in the right direction, right, of where your problem is. And API and priority and fairness, like we talked about, Sai, it's easy to over-index on that, realize the problem somewhere else, and you get into trouble. Let me give you a great example. Here's how you know if a chart is kind of leading you to the problem or away from the problem. This is called a heat map. And what this is it's saying, hey, how many of these requests were delayed? And sorry, this isn't like super great, right? Maybe I've got a better example in the blog here. But what I can do easily is say, hey, wait a minute. Here we go. I have some API duration that's kind of getting a little late in here, right? It's half a second. Is that a problem? Well, now I can kind of scan over to the etcd and say, wait a minute, that latency that I'm seeing is actually etcd. It is not, right? I can go to etcd request and see that the latency that I'm seeing is actually etcd latency, not API latency. And you know what that would do, Sai? That would make sure that I wasn't troubleshooting the wrong thing. Does that make sense?
Yeah, that makes sense. And I did put a link to this dashboard in the chat here. So, obsessive might not be entirely accurate here, but if you need to figure out what's going on here, get to the bottom of the issue, these dashboards do seem very helpful.
And I mean, to this point, like the graphs and the metrics can point you in the right direction for those fixes. Just like Shane's saying, like, I'm not going to go to the mechanic if I have a toothache. Or like some people are looking in the complete wrong place for the answer because they just think like, oh, they fix things or this area is the right area to focus. And they just start diving in deep and they make assumptions about that problem. And being able to have the right data and understanding the system more holistically will help you so much to dive into only the correct areas to find the solution to what you're actually facing. Or even if it is a problem at all with something that like it might be your workloads, right? Like we keep saying over and over again, like Nathan's demo, optimize your workload, how you're calling the API, and don't try to fix the API server, right? Like don't just, I need the largest API server available because I need to do list calls at 50,000 secrets. Like, well, maybe you don't. Like, let's see how this actually works.
Where were you when I first started, Justin? That was half of all wisdom in Kubernetes in like 1 minute, right? So yes, 100 times yes on that. Let's also go through kind of like a little bit of futures on what this thing was supposed to do. So this is, they work in sprints, just like any software development cycle. This was the first place that they stopped to give us something to fight against this, bad client just going crazy. But where they really want to go is the following. They want the system to be adaptive. Because if you think about it, etcd is kind of like the linchpin of all of this. What they want API and prior fairness to do is to be adaptive of whatever rate that your etcd can take. It's going to send signal, right? Maybe slow applies, whatever that etcd sends, to let dynamically API priority and fairness adjust that safety valve to protect that etcd for good working order. When they did this originally, that's kind of their vision. And I think that's a brilliant vision. It's just taking a little bit of time to get there for obvious reasons, right? So if this seems overly complex at first guess, it is, right? This is meant for people that need to tweak some stuff out, but realize where they want to go is going to really take Kubernetes up a level, right? Because once you've got that safety valve correct, you're going to get better performance and stuff out of the system. So, just as an aside on kind of the big picture there, if that makes sense.
Yeah.
With that, guys, I'd love to just maybe take some questions or, we can kind of just open the floor. I think that's all I wanted to share from just a simple, here's some dashboards that I got. If you find that useful, please do check out the blog. If you have any feedback, as always, let me know. I'd love to hear from you.
Yeah, and I know we do actually need to wrap up right now. We're reaching our time. And so the two things that I love so far that Shane, you said early on was you're only one Helm deploy away from hitting this problem, right? Like that's people deploy these things and they don't necessarily understand them. And it is essentially a curl to bash in a distributed system is probably a bad idea if you don't know how the system works or what you're deploying. And that's really something that we try to show on this show over and over again with demos and help people understand the systems they're running and how they work. So you can know where to get help and how to learn these things a little more deeper, a little more than the YouTube short from here's 1 minute to explain it. We just spent an hour and we're still not even like in depth of what you could go into.
Which by the way, Justin, apparently, I thought you used a voice modulator or something to do the Elmo and Ernie voices. Apparently, this is a skill that you just have. You can do an Elmo voice.
Yes,
got that range.
Elmo comes out for my kids all the time.
That's great.
Yeah, this is a common thing in my family, and I've learned a lot of voices with a couple kids. So
That's awesome.
But anyway, thank you so much, Shane and Nathan and Sai, for joining. Thank you everyone who joined the live stream. If you want to dive more into this, feel free. There are people, I know a lot of us hang out in Slack. There's a Kubernetes Slack that some people are active in. Look at eksworkshop.com if you're trying to learn Kubernetes and want to get started. There's a ton of great tutorials on there. And then also, we didn't link to the EKS best practice guide, but we do have best practices that go into a lot of this detail on various topics, such as AFP, but also scalability in general and various other areas. So check out the best practice guide because those are all amazing resources that we try to group this stuff together so that you can find it on your own whenever you need to. So there you go. Thank you for linking that.
Got it.
And with that, we'll go ahead and wrap up. Thanks everyone for coming and hope you have a great day.